Okay, so taking a look at our quiz number 3 review. Tomorrow's quiz, here is our review for it. One of the things that you were asked to do for the first 4 problems was it stated which statements are true about the polynomial. So one of the things that you were asked to do is that we talked about yesterday is that we're talking about the number of terms, what is the degree, what are the names of those things. So what we're looking at here is number 1 is that these must be written in standard form before we. So one of the key things that it has to happen is that if you are going to evaluate it, one of the things that you have to do is number 1, we have to make sure it's written in standard form. What does standard form just mean in plain English? Highest exponent first. And if there's any like terms to be combined, combine them. So remember we talked about the leading coefficient. You might be asked for the leading coefficient. That's the number in front. So in this first case, what is the leading coefficient? 3. The number that's right out front of the highest exponent. All right. So the leading coefficient is 3. We've got 3 terms. Remember, terms are separated by plus or minus signs. So if the terms are getting you, what I usually do is circle the plus or minus signs, and then I just underline everything else, and I see how many terms there are. So remember that chart that stated, like, what do we call a first degree term, polynomial, a second degree polynomial, third, fourth, even something to the 0 power all had names. And that's where we're getting this quintic from. Something to the 5th power, like a 5th degree polynomial, is called a quintic. And in this case, there's 3 things, so quintic trinomial. So that's what we are doing through 1 through 4. So I've got those up there. Any questions on 1 through 4? I'll leave those up there so you can just take a minute. I'll pause the video here and you can take a minute to look at those. Let's do something kind of tricky here. Let me just make up one for a moment and let's take a look at it because I'm going to try to throw at you some things that I think would be more difficult. Let's say I've got... Let's say it's something like that. First of all, how many terms do I have? 3 terms. And again, if you're not sure, just like circle the pluses and minuses, and you've got 1, 2, 3 terms. Which one of those has the highest degree? Somebody just throw it out there. You don't have to raise your hand. Okay, so 5x y to the 6th power. What is the degree of just that piece right there? 7. Why is it 7 and not 6? Because the x has a 1 on it. So when we're looking at just this term here, I say this because this is going to get somebody tomorrow. This is going to get somebody right there, and I would rather it not get you. So right there, that is a 7th degree. Now, we don't have a name for that. We didn't learn that. Don't worry. I'm just saying, what would you do in those situations where you have 2 terms like that? So after I've done this one, what comes next? 4x cubed y cubed. What is the degree of just that part? 6, because it's a 3 and a 3. And then finally, 2x squared y cubed. And what is the degree of that? Okay, so this is a 7th degree, which we didn't learn the name of, so you don't need to worry about it. But I just wanted you to understand that how do I get the degree? Well, you need to understand is that it could have 3 different variables that add up to 5, so that might be where it's coming from. But in this case, this is a 7th degree polynomial. When we get over 5, we tend to just use it's a 7th degree, it's an 8th degree, a 9th degree, 10th degree polynomial. All right, then for 5 and 6, it asks you to add and then subtract 2 polynomials. When we add, it's very straightforward. We're just taking these things right there, and we're taking the first 2 plus the second 2. So when it comes to adding, we don't really need those parentheses. So you'll see what happens is basically between the first line and the second line is we just dropped the parentheses. Like if you notice, the only difference was the color change and that the parentheses are gone. Then we combine like terms. Please remember that we do not change the exponents when you add or subtract. So 3x squared plus 4x squared is just 7x squared. The exponent only is going to change for us when we either multiply or divide. So that's where our 7x squared came from. And then we've got 1 plus 3 is 4. Any questions on that one? Everything here is what you will have to do tomorrow. Even though I said you didn't have to do those ones 10 through 12 because you didn't. Okay, so all we're doing is just adding them. So please, the key thing to remember is if you are seeing adding or subtracting of polynomials, you are not going to change those exponents. You will combine them if you can, but you will not change them. And again, written in standard form with the highest the highest exponent first. There we go. Now here's the one that becomes more difficult. This is the one problem that when we get to subtraction, it's not just, do not just drop the parentheses and subtract like you do with addition. In this case, this subtraction sign right here, this one right there, is being applied to each of those things. I have to subtract every single one of them. That's why I'm subtracting a 2x to the third power and subtracting an x squared, and I'm subtracting 2 right there. So that's where each of these things come from, because I'm subtracting each one of them. Or if you prefer to think of it as I'm distributing a negative to each one of them, that's fine too. It ends up exactly the same way. So once we've got it distributed, then we can do it just like we did the addition. I'm going to look for things that have the same variable, same power, which are these two right there. 9x to the third minus 2x to the third becomes 7x to the third. Negative 6x squared minus x squared becomes negative x squared. And then there's just a negative 2 at the end. Written in standard form, highest degree first. Any questions on that one? All right. This is being recorded now, so if you need to go back to any of this, it will be posted. You can go through the review later as well. So you'll have the answers. You'll be able to go through them. Okay, so 7 through 9 are again addition problems. Notice that the exponents do not change. It's when it comes to adding them, those are the super easy ones. You're just going to drop the parentheses and combine like terms. So all you really need to worry about at that point is, am I adding correctly? Sometimes I just check my numbers, I drop it, make sure I didn't change something from a positive to a negative, from a negative to positive, just leave it as it is, drop the parentheses, and then we're combining like terms. If I see 2x squareds, I'm combining them. If I see 2x cubes, I'm combining them. Yes, sir?
I think you have the wrong answer.
Yeah.
All right, let me take a look. Let's see. So we've got 11x squared and, so we've got, let me just make sure all the numbers were copied correctly, first of all. 5x, 4x. Okay, so we've got, yes, our first one is right here. So there we go. There's our 15x squared. Then we've got x to the third power plus 5x to the third power, which would then be 6x to the third power. So that really should be a 6 there. Good catch. Was that what you're referring to?
Yeah.
Okay, so that one should be a 6, x to the third power. Plus 15x squared. Let me just see, make sure we've got that minus 2x. We've got the plus 7, in which case it still is written in standard form with the highest degree first. What is the leading coefficient on this one? And if I had to name this one right here, that should be a 6 down here too. So let's just make that correction. So let's say that for some reason I had to name this. We know that the leading coefficient is 6. That did not ask you to do this. I'm just saying, what if this were a question? Leading coefficient is 6. What is the degree of that polynomial? 3. What do we call something with a degree of 3? Cubic. And how many terms are there? 4. It's a cubic polynomial. That's what we would call this. Those are the things that you might be asked on a question like this. When it comes to 8, because we are subtracting, now if you're like, wait, what subtraction is he talking about? The one that is in between the two parentheses, because I've got one parentheses minus another one. And when I'm doing that, that negative needs to get distributed to all the things on the right. That is why the negative 7x to the fourth became a positive 7x to the fourth, and the positive 11 became a negative 11. So that is being distributed there, in which case, again, combine like terms. We've got x to the fifth power, nothing to combine that with. Negative x to the fourth power and a positive 7x to the fourth power. That becomes 3x to the fourth power. And then a positive 1 and a negative 11 become negative 10, written in standard form there. What would I call this one? What is its name?
Fifth degree trinomial.
Interesting.
Wait,
A quintic trinomial, because remember, something to the fifth power is quintic. So I'm kind of a jerk about those names. I'm not talking about like spelling things, like if you accidentally spell it incorrectly, but I do this. If you spell it incorrectly, I sound out what you wrote, and if that's not the right word, then that's wrong. So I get it. Like, I'm not the best speller in the world either. That being said, I'm going to phonetically sound out what you wrote, and if that is like if it says quintop, then I'll be like, no, it's not quintop, it's quintic. You know, those are two totally different things. So if you swap the C for a K, that's not an issue for me. But if it doesn't have even the same pronunciation, then that is a problem. Number 9 gave you a problem that looked like this, and it told you that x is equal to 100. So a lot of times that this gave people a problem because they're like, wait, what do I do with this side over here? This just means that there is a function. For example, c of x is the exact same thing as like y equals, and we've got x to the third minus 15x plus 15. And all they were asking you to do was plug in x is equal to 100. That's what they want. They're like, x is equal to 100. You plug it in and figure out what you got. In which case, we've got 100 to the third power there. 100 times 100 times 100. That is actually not something that should take you on your calculator. Like, it shouldn't be something you have to do on your calculator. And if you're like, wait, what, you can do that without a calculator? Sure, you can too. Because one of the things that you know, if you haven't learned this yet to help you out, tens are super easy. Anything that is like a base of 10, like 10, 100, 1,000, they actually should be pretty easy to multiply. Because if I do 10 times 10, I already know that's 100, right? Like, so if you're not sure there, I just know that I'm going to have a 1 with 2 zeros on it. So we end up with that. So we've got a 1 with 2 zeros right there. Same with multiplying 100 times 100. In this case, I'm going to have a 1 with 4 zeros on it. 1, 2, 3, 4. But now I've got times another 100, which picks up 2 more zeros. In which case, it becomes 1 million. I'm not like a math genius to do that. I'm just doing what it says, just like 10 times 10. So we're going through it just like that. We plug in when you work it all out there. It's not terrible. It's some big numbers, sure, but actually the subtraction is very easily done by hand. It's just a lot of digits. It's not like any of the math is terribly hard. Now, 10 through 12, you were not asked to do because we haven't gone over graphing those on a calculator, but here's what I would expect. On 10 through 12, if I gave you those graphs, I would expect you to identify how many real zeros there are. And those real zeros, remember, is how many times does it touch the x-axis? Only the x-axis, not the y. So in this case, it is 2 real zeros because it touches it 1, let me switch colors here, 1, 2 times. It can touch it, it can cross it, but every time it touches the x-axis, whether it's going through it or just tapping it, then we get a 0. So in this case, we've got 2 real zeros. In this situation here is our x-axis. We've got 1, 2, 3 real zeros. And in the last situation where it never crosses, I have no real zeros. Don't say no solution, things like that. We're just saying there are no real zeros. Yes, ma'am?
How do you graph the number or the equation?
That's right. So you're not going to have to graph it. Like, that's the part is I will give you those graphs and I will expect you to be able to identify the zeros. So we are going to get into that. Your question is a valid one. We're just not there yet. So we will get there. But for now, you're just going to be interpreting graphs, saying how many real zeros are there. All right. So 13 through, let's just look at 13 through 16 for a moment. We've got a lot of distribution here going on. So if it doesn't say to use Pascal's triangle, then it usually means that it's probably just a little bit easier to do it by hand, that you can work it through. Like on 13 and 14, that's just distribution. That's like going ahead and distributing it. Some people call it foiling, but foiling really only works when there's 2 binomials. But I get what you mean. Sometimes people say foiling and they mean I need to distribute. So on 13, you can see that the 2y has been distributed to each of them. Now remember that when you multiply two things, if they have the same base, like they're both x's, then I am going to add their exponent. In this case, I've got a 2y multiplied with a 4x squared. They are not the same bases, so that's why neither of the exponents changed. However, when I did 2y, the second part, plus 7xy, the 2 times the 7 became a 14. The x had nothing else to multiply with, so it's just an x. But those y's became a y squared because y to the first power times y to the first power. When that part happens, we get y to the 1 plus 1, which is y squared. That's only going to happen when you multiply. That's you're adding the exponents there. That only happens when you multiply. So if you are changing exponents, like if you're stuck and you're changing exponents, you better have multiplication going on there. Yes, ma'am? Oh, you're just checking your glasses, sorry. Any questions on 13? Okay. 14, again, distribution. This is two binomials. This would be foiling. But really what it means is both of the terms on the left need to be multiplied with both of the terms on the right. The a needs to be multiplied with both of them, and the b needs to be multiplied with them. So that's what we're seeing there is the two distributions. The a times each of those things, then the b times each of those things, in which case you can see that a times 3ab became 3a squared. The a's had both had 1 on them. 1 plus 1 is 2. When we distributed to the b, it just became ab squared. They combined. Over here, when we did this first distribution here, 3ab times b, well, those b's are going to combine. A 1 and a 1 become a 2. And a 1 and a 2 become a 3. So that's where all this is coming from. And then we're going to see if we can combine any like terms. So let me just take a look here. 3a squared b, this one right here, has nothing else to combine with right there. But this a squared b plus 3a squared b, now careful because it says we're adding them. ab squared plus ab squared. I think I said a squared b. I meant to say ab squared plus 3ab squared. If I have 1ab squared plus 3 more ab squared, I just get 4ab squared. Because I am adding, that is the reason that the exponents didn't change. And then finally, b cubed has nothing else to go with. Questions on that one? Yes, sir?
For those questions, can we leave it like that or simplify?
Here, there's no more simplifying to be done after that pink line. Here, on the green line?
No, never mind.
Okay. Okay. If you managed to get to the green line and you had stopped there, you definitely would lose half points for not finishing. But you certainly, I think that's worth something. Everything is correct up to that point, so that's worth something. But don't just count on like, oh, I'll get by on half credit. All right, so here we go. When we've got 2x plus 1/3, that quantity squared, then we're going to go and we get 2x plus 1/3 times 2x plus 1/3. Could there be fractions? Sure. Yeah, like we're at algebra 2 at this point. Let's stop pretending that everything out there is a whole number. Most things in this world are not a whole number. Whether you like it or not, your age is not a whole number. You may call yourself a certain number. I may call myself 41. I'm 41 in some fraction. There's only like a minute moment that I'm exactly an age, and then it's gone forever. Then all the rest of the time I'm fractions. So we've got 2x plus 1/3 times 2x plus 1/3. Remember when you multiply fractions, like when I get to the 1/3 times 1/3 part, that's going to be just like this. 1/3 times 1/3. Right across the top becomes 1. Right across the bottom becomes 9. That's where the 1/9 came from. And when you get to the part where you're multiplying whole numbers times fractions, just remember that 2x is a fraction as well. 2x times 1 is 2x divided by 3. That's where the 2x divided by 3 came from. But actually, when we do all the distribution, we end up getting 2 of those. 2x plus 3 plus 2x plus 2x over 3 plus 2x over 3 becomes 4x over 3. 2 of something plus 2 more of something becomes 4 of that something. Yes, sir?
How come you didn't change it to 1 over 3x?
You could use a mixed number too. It just looks a little weird with a variable sometimes. It tends to get lost in there. So I can tell you this. A lot of times people go and try to turn things into decimals. And I get it. Like, people seem to like decimals for whatever reason. I can tell you that, like, doing math for a while now, I can tell you that I very much dislike decimals. And I'll tell you why. It's extra work and more possibilities of making mistakes. And sometimes those decimals are way harder to multiply. You may not like fractions, but in most cases they're way easier to multiply. So if it were in a mixed number and I still had to do some multiplying, then I can't use a mixed number. That's why I tend to leave things just like this, in this case, an improper fraction. Okay, so on these ones, these get pretty big. 16, again, everything on the left needs to be distributed with everything on the right. So what's happening here is this. Boom, 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 boom. But then the second one has to do the same thing. Boom, 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 boom. I'll tell you why this one's a problem, is because let's face it, even if you know exactly what you're doing, that is 4 distributions on top, 4 distributions on bottom. That's 8 times you have distributed. That's 8 possible times to make a mistake. So that's the line I would always check, is that when I start doing that distributing, I would check all my numbers right there, because I just did 8 distributions, and if one of those numbers is wrong, it's going to make my end answer wrong. Yes, ma'am? Okay. So again, when you are distributing, you are multiplying, so that is why our exponents are changing. We add their exponents. If I've got the same base and I am multiplying them together, then their exponents are being added together. So I'll give everyone a minute on 16 to take a look at it. Any questions on 16? Yes, ma'am. 6x squared came from this one right here being distributed to this one right here. 2 times 3 is 6, and x times x is x squared. So that one times that one became that one. Any other questions on 16? Okay. Here's where we get to Pascal's triangle. Now, here's the main thing. If you can't construct Pascal's triangle, you can't do Pascal's triangle because you've got no place to start. So, again, I don't need you to create this over and over again. Just create it once as a little reference tool. But let's say that I wanted to build Pascal's triangle right now. What would you tell me to do? A triangle out of ones. So let's do that. And that just means like put a triangle, put a 1 in each corner. There's a triangle made out of ones. And then what? 1, 2, 1. Where did I get the 2 from?
1 plus 1.
So right, this 1 plus 1 right there. And then what's my next line?
1, 3, 1.
And again, these 3's came from the 2 right above it. The 1's will always be flanked, the sides will be covered by 1's. So I can keep going as far as I need to. I don't know how much I'm going to need. In this case, I need the 4th level. So here is something to the 0. Start at 0. Don't start at 1. Because if you start at 1, you're not counting for things to the first power, to the 0 power, which always equal 1. In this case, something to the first power is right here. The second power is here. Third power is there. Well, if this is 4th power, I need one more line. So 1, then what? 4, 6, 4, 1. That's the line I need. So that's where those numbers came from there. I am going to actually erase that off of mine so that it's not covering the actual answer there. But just to show you where, I'll redraw it up here. Here we go. Let's go 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. So there's Pascal's triangle, at least to the 5th level there. So that's where our numbers are going to come from. Now, if you notice, in each case, they each got an x. They each got a -3. That's a -3. So the x's decreased in power, x to the 4th, x to the 3rd, x squared, x to the 1st power, x to the 0 power. But the second term, the -3, increased by 1 each time. 0 to the 1st. -3 to the 0, -3 to the 1, -3 to the 2nd power, -3 to the 3rd power, -3 to the 4th power. So then we've got our terms right there, which the first one, when I worked those out, just became x to the 4th. Then we've got 4 times x to the 3rd times -3, which became -12x cubed. 6 times 9 is 54 with an x squared. 4 times -27 is -108 with an x on it, and then just 81. What if I had to name that polynomial? What would we name it? Close. Quartic. So think about it like, here's how you remember 4. There are 4 quarters in a dollar. So like you're going to go quart. Like it's like 4 quarts in a gallon, like 4 quarts. That's like that 4th there. So quart. Think quart. It's quartic. But quartic polynomial because there are 5 terms. Last but not least, we've got another, on this page at least, we've got another Pascal's triangle. This one is to the 3rd power, so here is 0, 1, 2, 3. That's where the 1, 3, 3, 1 came from right there. And then we attach the x to it. We attach the 2y to it. We throw on the exponents. And I'll give everybody a minute, and I'll take questions on this one in just a second. You good?
Yeah.
Okay. All right, last but not least, we had two more. One of them was the one with the box, like you had a box and you had to figure out the polynomial that represented the volume. Well, remember, volume is length times width times height from geometry. It's like if you've got a rectangular prism, then it's length times width times height. So you just had to multiply the three things together. That's 20, length times width times height. So just distributing there. So what you're seeing there is the distribution. And over on 19, again, Pascal's triangle. 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. That's for things to the 0 power, to the first power, to the second power, to the third power, and to the fourth power. So that's why we're using it, because this is to the fourth power. That's why we chose this line. In which case, we started with that line. We added a 4x to each one of them. We added a -1, and then we started with the 4x, and with the 4x, we went 4, 3, 2, 1, 0. With the -1, we went 0, 1, 2, 3, 4, leaving us at our bottom answer there, 256x to the fourth power minus 256x to the third power plus 96x squared minus 16x plus 1. So lots of little areas here. There's a lot going on. So it's got to be the kind of thing that you practice and not tried to like cram last minute. Any questions on 19?
For 20, I'm not gonna have a question on the first test.
It very much could be. I mean, that was just like a multiplying. The hardest part of it is whether you remembered how to find volume, but it's one of those things that like we've done that a lot, especially last year in geometry. That's one of the biggest things that you do is calculating volume and surface area. All right, I would take time and make sure I know how to do these. If you are struggling on any of those, if I said something to you and you were like, I don't even know how he did that, go back to YouTube and watch those videos. That's why I record them. They're there for you. Like, I don't record them for me. I already know what I sound like. You can go through them and rewatch anything and get you caught up. I am uploading this right now, so you'll have those answers and you'll have this available to you as well. I'm gonna put it on YouTube. Yeah, I don't want to do the YouTube and then post it again too, because I'm just doing it the same thing twice, but in different formats. So you can just go through it and look at there. Yes, ma'am?
If we did like width times height times length, would that be the same answer?
It's such a great question. She's got a legitimate question. So she said, what if I did width times length times height? And so let's say that you've got this question, you're sitting there in your mind mulling that over, like you're like, I don't know if that's true or not in your head. The way that I figured out how to get through this situation was that I go, okay, let's pretend that I've got three numbers, 2, 5, and 4, and I'm about to multiply them. Let's see if the order of multiplying changes. 2 times 5 is 10, times 4 is 40. So that gave us 40. Let me try it. 5 times 2 times 4. 5 times 2 is 10, times 4 is 40. Let me try 5 times 4 times 2. 5 times 4 is 20, times 2 is 40. So now I'm going to try 2 times 4 times 5. That becomes 2 times 4 is 8, 8 times 5 is 40. And then I've got 4 times 5 times 2. 4 times 5 is 20, times 2 is 40. And then last but not least, the only other possibility, 4 times 2 times 5 is 8 times 5, which is 40. So I'm not trying to be funny. I'm trying to be like, let me just show you like logically, if you ever get stuck there, how you could come to that answer yourself. So does it matter the order in which you multiply them? No. So, and that is true for when you are adding and when you are multiplying. It is not true for subtraction and division. Because remember, 5 minus 3 is not the same as 3 minus 5. We get two different answers. But adding and multiplying, the order in which we do it doesn't matter. As long as we obey our order of operations, we have to do certain things first. Like if there's adding and multiplying, well, the multiplying has to come first. That has to be done first. So just always stick with your order of operations and then go left to right.